measurements, and the rest is known to us more or less. So it means we have to look into how solar radiation is reaching the Earth's surface and how it is manipulated or controlled by Earth's surface to form different ways. To start with, electromagnetic spectrum, which the word itself says is a spectrum, is a large span of wavelengths or frequencies. You can say there are infinite sine waves having different time period or frequency, wavelength, etc. Similarly, electromagnetic spectrum would account for Earth's radiation, solar radiation, gamma rays, X-rays, microwave, all these things. Out of that, this small part, this tiny spot which you can see in colors is the visible spectrum, which is what we can see. It is nothing, it's like putting some salt into an ocean. It's a very small band in the entire infinite spectrum. Out of this small band is what we can see. So everything that we are talking about, we are thinking about is coming into this small narrow band, which comes up from 400 nanometer to some 700 nanometer or 750 nanometer. And everything that we are talking about would be centered around this ultraviolet and infrared. This is what we are talking about. And when we talk about visible radiation that we can see, you should also keep in mind that there are a lot many more wavelengths which we cannot see. Only the small portion is what we can see. The rest you cannot see. It's just like seeing this picture. On the left side is what we see with our eyes. On the right is what we are seeing, not with our eyes, but with some infrared camera. You will see this in airport security check and all. What is happening on the left is visible light is reflected from that person and all those things and coming back to your eyes. You can see that. Your eyes sensors can take it. On the right side is some thermal emission coming from these bodies. Your eyes won't be able to see it, but interestingly, what was opaque in the left side is visible on the right side. So if you have a sensor which can see in that particular wavelength, you will be able to get what is there. Your eyes won't be able to see infrared, which is why you are not able to or go through that black. But inside that, if you have an IR camera, you can see what is inside. So the point is, same process should be connected with our Earth atmosphere system as well. When you look on the right side, what you can see is a pure white surface, which is some snow or ice sheet. To the left of it, you will see dark blue or dark colored ocean. This means it is white in color, snow is white in color or ice is white in color because it is reflecting off all wavelengths that you can see, visible light. But it doesn't mean that all wavelengths that is coming from the sun is reflected off. There would be some radiation like ultraviolet or infrared, which is not seen to us, which could be absorbed by ice or snow. A good amount of light coming from the sun, which forms visible, is reflected by this ice. Another good amount of radiation which you cannot see would be absorbed. So snow being or ice being white doesn't mean it is not absorbing anything. It is absorbing. If there is change in long wave radiation, or we'll come to that, some radiation that you cannot see, this may absorb radiation and it can increase snow melt or ice melt. So this should be kept in mind. Now to explain all these things, we'll come back to this very fundamental picture. On the top, what you are saying is emission coming from sun, which is the so-called equivalent of a Planck's black body emission spectrum. We'll come back to that soon. On the right, the small peak is the radiation which is emitted by Earth's surface. What happens is solar radiation comes from top, enters the Earth's atmosphere, reaches the surface, and some part of it would be absorbed by Earth's surface. Then it gets heated up, right? Earth's surface gets heated up, and then it will start emitting some radiation. Any surface or body which is at temperature greater than 0 Kelvin would emit radiation. So Earth, since it is not at 0 Kelvin, will also be emitting radiation, and that comes out in this range. So this top curve shows you what is the radiation emitted by the sun and by the Earth. You will see that for solar radiation, good amount of that, about 50% of that is coming in the visible radiation, which we can see. To the left of that, which is called as ultraviolet, is something that you cannot see. To the right of that, again, near infrared is again what you cannot see. And Earth's emission is totally opaque to our eyes. Okay. Now the other figures which you can see below are the absorption spectrum of different components or species in the Earth's atmosphere. Top one is ozone or oxygen. If you see a black color here, it means it is absorbing radiation to that much level. So when you see a totally black region here, it means this species, which is ozone or oxygen, is purely absorbing in ultraviolet region. Have you read that or come across this anywhere? Ozone absorbing ultraviolet? Yeah, you have read about the ozone layers, right? So this is happening here. Ozone up in the stratosphere would be absorbing almost all of ultraviolet radiation coming down. So this acts as a blanket to us. So we don't get ultraviolet radiation to a good extent to our surface, otherwise which would have been harmful to us. So what is left is, you will see that in ultraviolet, you don't see any absorption by carbon dioxide or water vapor. Ultraviolet absorption is controlled purely by ozone. Now when you look into visible radiation, you will see that ozone or oxygen is having some absorption, but not too much. CO2 and water vapor is not also having much absorption there. And if you extend to this region, which is called near infrared, which also forms part of solar radiation spectrum, you see oxygen or ozone not absorbing anything, and CO2 having slight absorption to the far end of near infrared spectrum, and water vapor having some good amount of absorption bands there, which makes the total atmospheric absorption totally opaque to ultraviolet, almost totally opaque, and mostly transparent to other parts of solar radiation, except for the some bands caused by water vapor. Okay, so water vapor is not considered as a serious issue when we are talking about absorption, global warming, etc. Do you see in any newspaper that water vapor is causing global warming? Do you see that? Textbook it is there. You can see from this plot also that black color shows it is absorbing, right? More than carbon dioxide, it is water vapor which is having more black colored absorption bands. So it means water vapor should be blamed, but we don't blame water vapor. We see in newspapers that CO2 levels are increasing, CO2 levels should be controlled, but nothing about water vapor. Why do you think it is not discussed?
Not the difference. Doesn't raise a lot of. It's not very eye-catching to blame water.
It's not that. What else could be the reason? How do you see water vapor getting transformed after some time? Water vapor is present in the atmosphere. Rain comes down. There would be some water in the surface, maybe pond or ocean or something. It again evaporates. So it is part of a larger water cycle, which is a natural process. And this will happen in a couple of days' time or hours' time. So whether you take care of that or if you control that or nothing, it's a natural process. It won't reside in the atmosphere for a long time. So even though it is having a lot of absorption bands, it will not be present in the atmosphere for a long time. So you don't really have to worry about that. And this is not really anthropogenic source. This is a natural process. But compared to that, CO2 or the so-called other greenhouse gases will stay there for years, hundreds of years. It means if you are emitting CO2 now, it can stay in the atmosphere for 100 to 200 years. Even if you are stopping all CO2 emissions right now, it will be purely gone only after 200 years. So that's the extent of which CO2 can induce global warming or greenhouse effect, etc. So even though vapor is the strongest greenhouse gas, we don't have to really worry about that because its lifetime is very less and it is part of a natural cycle. Okay, so we don't really talk about water vapor, or we don't have to worry about water vapor when we talk about these things. That being told, no other gases in the atmosphere would be having lot of absorption in solar radiation spectrum. You don't see much black bands here. So you can consider solar radiation to reach the Earth's surface from the top almost purely transparent, like almost 100% of it would reach the Earth's surface except for this ultraviolet. This is what we say that solar radiation will reach the Earth's surface without absorption. First part.
This will be 40% out of 100, no? This radiation which will be.
Which part?
Complete solar radiation, 40% is coming to Earth.
Not 40. When you say it is about 30% of planetary albedo, roughly, which means 30% would be reflected off at the top. At the bottom, it would be some amount. It depends on what is atmospheric constituents as well. But you will say that at the top, 70% is coming down. 30% may be reflected off. Top of the atmosphere, we'll usually say it has some 100 kilometer height. So it's a net effect of water clouds or aerosol particles or anything is present means they all would be contributing to it. At any point of time, we usually take 30% as reflected off, 70% would be coming down. And what reaches the surface depends on what is in the atmosphere. Now what we have to see here is, if solar radiation is reaching the Earth's surface, there are multiple possibilities for that. If radiation is incident on a surface, what could happen? It could either be reflected, it could either be absorbed, or it could go through it, which is called as transmittance. This transmittance is very less for surface or soil. The processes remaining are reflection and absorption. Out of this, let's say that some good amount is absorbed and then the remaining amount is reflected off. If there is some reflection happening, the remaining amount is all absorbed. If something is absorbing some radiation, it could raise its temperature. Like if you're keeping your hand under some incandescent light, you will feel some warmth because your body is absorbing that radiation. It is increasing your internal energy, which is finally used in elevating the temperature level. So this means Earth's temperature would increase. Or this also means Earth is having a non-zero temperature because solar radiation is being absorbed. If there is temperature greater than 0 Kelvin, it would emit. Like sun is also emitting like that because it's having a temperature of 6000 Kelvin. Similarly, Earth would be having a temperature of about 300 Kelvin, 27 or some 18 degrees Celsius or something. So it would emit radiation. Not just Earth or sun, we all are emitting radiation. We are all having some temperature greater than 0 Kelvin. Okay. So this means Earth would be emitting radiation and it corresponds to this particular spectrum. The point that you have to see is Earth is not emitting in visible range and Earth is emitting in a what is called as a far infrared range, with its peak emission happening around 10 micrometer or so, 10 micrometer wavelength. Now when you look into the absorption bands again, ozone or oxygen is more or less purely transparent except for this peak. Carbon dioxide is having a huge absorption band here. Around 14 micrometer, it is almost 100% absorption, and around 4 micrometer also, it is almost 100% absorption. This is a strong CO2 absorption band. Water vapor is also a culprit here. It is blocking almost all radiation, and beyond this, don't even think about it, it's gone. So this means Earth's emission may be getting absorbed, or it could get absorbed when it is trying to escape out. This is the radiation which is going up from the Earth's surface, and it would be going through the Earth's atmosphere. Now what happens then? Carbon dioxide will absorb, water vapor will absorb, and so many other so-called greenhouse gases will absorb. This prevents all the radiation emitted from the Earth's surface to escape out. Some of them may be getting absorbed by the Earth's atmosphere. If it is absorbing, it will again increase its temperature, which is what we call as a greenhouse effect, an equivalent of what happens in a greenhouse, which is used to keep plants warm. It allows radiation to come inside, but it doesn't allow all radiation to escape out. This is also what happens when you're going inside a parked car under daylight. Glass is there, it lets sunlight in, it doesn't let the infrared radiation escape out. So the temperature inside the car increases. So similarly, because of all these things, some of the radiation is getting absorbed and it increases the temperature, which is what we call as the global warming. So solar radiation is let in almost fully. Terrestrial radiation is not let out fully. Some part of that is absorbed. This is greenhouse effect and the resulting temperature change. Please keep this in mind, and we'll come back to this explanation again after some time. Please stop me if you're having any doubts or if you want to ask something.
How this graph formed?
This graph, the top one. So this is mostly like a black body emission spectrum. I'll explain that. By the end, I will draw these things. These graphs are characteristic of that compound. If CO2 is like that, it's a property of CO2. You have to get a spectrometer or some way to figure out these things. This won't change. It's a signature of that species.
So the incoming solar radiation from the sun, you are saying 30% might be 30% of the total solar radiation might be reflected back at the top of the atmosphere.
Right.
The rest 70% reaches transmits to the atmosphere and hits the Earth's surface. Now the Earth's surface would absorb some of it?
You can consider like this.
Uh,
This is Earth's surface
Yeah.
and this is top.
huh.
If you're looking from top, some 30% would be
Yeah.
gone. It may be reflected from here, here, or here, but you're considering that the entire atmosphere reflects 30% of it.
Yeah.
70% may go down.
Hmm.
And out of that 70%, some amount may reach the surface,
Okay.
depending on what is in the atmosphere.
Hmm.
And whatever is reaching the surface, some part of that would be reflected by the surface and rest would be absorbed.
The absorbed radiation will again be emitted back.
Absorbed radiation would increase the temperature and it would emit in another wavelength.
Okay.
It is not the same wavelength. You have to see that there is a wavelength change in this emission. Greenhouse effect is not caused by reflected solar radiation. It is caused by re-emitted radiation. Keep this. So just an analogy of what is happening in a greenhouse effect, which you have already told, and you can check this graph later. This is an essence of what we told. So yeah, I wanted to explain something in writing. I was not sure if a board would be there. Maybe I can explain with this itself. So I have written something there. Can you read whatever I have written there? Okay, you read there. So we are trying to see what happens when radiation is propagating through the atmosphere. Okay, what is happening to the radiation? We told some 70% is available to reach the surface, but then it has to pass through the atmosphere. When it passes through the atmosphere, what happens to it? This is what we are trying to explain here. Now consider this as equivalent of an atmosphere but kept in a horizontal manner. Instead of this, we are keeping it like this. And this is the radiation which is incident. And this is the radiation which is escaping out. We are trying to figure out how much radiation would be lost in between this medium. Okay, so consider an infinitesimally small slice of this medium, a small rectangular piece, and we want to figure out how much of light or would be intensity would be lost, which is di. Di is the change in intensity of light as it propagates through an infinitesimally small medium of length dz. Okay, we are trying to figure it out. So what would this depend on? Di. Di is the light difference. Anyway, when it is passing through a medium, it won't be higher, right? If you're sending light from here, do you expect light to be more at the other end? You don't get that. Basically, there will be a 1 by r square loss, and there is no reason for it to increase unless some other conditions arise. So this di should be a number which shows a reduction. Di should hence be associated with a negative number, negative value, because it is coming down. So you will see that di by dz, the difference in intensity as it passes through an infinitesimally small distance dz is proportional to I. I is the incident light. So why do I write this? Suppose there is a medium and I am sending 100 photons from here, or 100 packets of light from here. You will get some 80 at the other end. This means 20% is lost in between the medium. 20% is lost. Instead of 100, if I am sending 1000, what would happen? You would get 800. This means if the number which is sent from here is larger, the number you can get at the other end will also be dependent on that, keeping the property of the medium same. It would depend on the incident light. So that is why we are writing di by dz is proportional to I. If I is larger, how much is lost in the medium will also be larger. Very simple, because it's a property of the medium. And this negative is coming because di is decrease. It is not increasing. So it is associated with a decrease. So you are keeping di by dz proportional to minus I. Now to remove this proportionality, we bring in a constant k ext, which means my equation would now be di by dz equal to minus k ext into I. And this constant which removes this proportionality is called as volume extinction coefficient. As the name says, it says how much light is getting extinct when it passes through the medium.
Means getting the loss.
Loss, right. How much light is lost when it passes through the medium. This is a property or feature of that medium. So this is the parameter that we will be interested in, presenting or representing how much light is lost when it passes through a medium. So you have to say what is the extinction coefficient or volume extinction coefficient of your atmosphere when you want to calculate how much light is reaching the surface. Okay, so this is the property that you want to see. And how do you think light would be getting extinct when it passes through a medium? It can get absorbed. We already seen that. It can get scattered. When you are sending light, it may go to some other directions. So there are two processes which can happen: scattering and absorption. And what we'll do now is, instead of this derivative kept here, we'll try to present it in an equation. Right? We will come up with an expression which makes more sense. We'll integrate this di by dz equal to minus kx into I. We'll just rearrange the terms. Di by I equal to minus kx into dz. And the limits are: incident light is I0, IZ is the light reaching the other end. To explain, this is the incident light. So your integration for intensity is from I at this end to I at this end. And integration for the distance is from z equal to 0 to z equal to length L. Okay, which is what I have written here. I0 to IZ and z equal to 0 to L. When you do this integration, you get this expression, which is the so-called Beer-Lambert law, which you may have studied in many other places as well. If you are studying chemistry, you will see that. If you are studying electromagnetic radiation, you will definitely see this, which tells you how much light is lost when it is propagating through a medium. And it would depend on this parameter, KEXT, extinction coefficient. You will see another term here, IISER, which is the light reaching the other end, equal to I0, which is the light incident at the medium, into exponential minus kx into L. Out of this, you can represent this KEXT, which is extinction coefficient, as sum of two terms. There are two things contributing to it, which is scattering and absorption. So you can represent this as scattering coefficient plus absorption coefficient. These are both properties of the medium. So you would be trying to calculate what is the scattering coefficient when you're talking about clouds or aerosol particles or even rain droplets. What is the scattering it is causing? How much absorption is it causing? When you are getting a summation of that, you are getting the total extinction caused by that particular medium. Now once you have this, minus kx into L, which is Ex into L, kx into L, is a term called as optical depth. Optical depth.
So which the entire exponential, which is the optical depth?
Not the entire exponential. What is in the exponent of this exponential? Kx into L.
That is optical depth.
Kx into L is your optical depth. Or to be more precise, this would be your optical depth. Integral Z1 to Z2, Kx of Z dz. Because if you are looking into atmosphere, this Kx won't be constant across the entire atmospheric column. It would vary with height. So you have to integrate it with keeping this point in mind. So Kx into L would be your optical depth, and e raised to minus Kx into L is what is called as transmittance of the medium, the atmospheric transmittance. So it finally reduces to a very simple expression, I equal to I0 into T, where T is the transmittance. So this is a very simple way of representing how light can get lost or extinct when it passes through the atmosphere. You can represent using two terms, scattering coefficient and absorption coefficient. Is that fine? Okay. Now, to characterize how scattering or absorption, or scattering, how it is happening, absorption we have already seen in the first slide when we talked about absorption bands. It is more or less known to us, but related to that, scattering is a more complex phenomenon. The reason is, you are having a particle here or some scatterer here, light is incident, you are trying to figure out how light is redistributed in all directions. This is what we want to know. So if you are having a scatterer or a particle here in the center, this dot that you are seeing here is supposed to be the scatterer. It may get redirected in all directions. Right? If your light is particle is like this and incident light is like this, it may go in all directions. Maybe I'll try to write it there. I'll do it after completing this part. I'll draw these things again in the board when I do that. What we have to keep in mind is, depending on the size of the particle and the wavelength of the incident light, the scattering would be varying. You have you heard about this terms, Rayleigh scattering and Mean scattering? So you would have studied that blue color of the sky is due to Rayleigh scattering, red sunsets are due to Rayleigh scattering, etc. So that's a property of the atmospheric gas molecules getting scattered by, or solar radiation getting scattered by this gas molecules. It won't be the same when you are having larger particles. You don't see a blue cloud, you see a white cloud, right? But you see a blue sky. Why is it so?
All the wavelength is getting scattered. All the incoming wavelength is getting scattered for cloud. That is why
Right,
it's appearing.
right. For sky, which is having gas molecules like oxygen, nitrogen, etc. in larger concentration, those molecules are very small in size. So they would be reacting to this solar radiation in a way which is different compared to cloud droplets, which are larger in size. Takeaway point is, depending on the size of the particle and the wavelength which is interacting with, the scattering would change. According to that, we are having different regimes of scattering. For gas molecules, we usually say it is Rayleigh scattering, but for solar radiation. For aerosol particles or clouds, we usually talk about Mean scattering, which is a general theory. Rayleigh scattering can be considered as a special case of that. Now, this is a plot between R micrometer, which is the size of the scatterer or the particle, and wavelength of incident radiation. This tells you that this is the only parameter that you have to keep in mind, just the ratio between R and lambda. R by lambda parameter, if you know, you can define how scattering in the atmosphere happens. You can see some basic picture here. You will get Mean scattering for a smaller wavelength, for a smaller size particle, but the same scattering can happen, which is this x equal to 1 line. The same amount of scattering can happen for a very large particle as well, but for a larger wavelength. Is that fine? If you are looking into only one particle size, say for example 10 raised to minus 1. For 10 raised to minus 1, at 1 micrometer, you are getting maybe around Rayleigh scattering. But if you are going to 10 raised to 5, you are going somewhere far above. So depending on the ratio of R and lambda, you can define scattering. So this is an entirely different topic on its own. If anybody is interested in that, you have a lot of domain open to explore. You can do this calculations for cloud droplets. You can see what is the scattering for aerosol particles, etc. Later when we discuss aerosol particles, we will see how scattering is approximated in such cases by considering various geometric parameters and all. So this is an entirely new topic or different topic on its own if you are looking into it.
So suppose our particle 10 micrometer. So which is getting very better like that. Many is getting strong.
Right.
So which one we will choose like that? Suppose
so if you are looking at 10 micrometer, this right.
Particle size. So
1 micrometer. Okay, for 1 micrometer particle, sir, for 1 micrometer is this.
Yes. And 10 to the power 2.
10 to the power 2, it would be roughly around Rayleigh scattering decay.
Sometimes it makes confusion.
Yes. So if particle size is very less compared to wavelength, you will get Rayleigh scattering. This is the simple thing that you can keep in mind. If particle size is almost similar to wavelength, you get this Mean scattering. And what you are seeing over here, these different patterns, tell you how light is distributed in different directions. If you see a pattern like this, which is a classic example of Rayleigh scattering, what you can understand is if the particle is here and light is incident like this, there would be equal amount of light getting scattered in forward direction and backward direction. It tells you that Rayleigh scattering, forward scattering and backward scattering are equal. This is, we can see mathematically, but we don't have to get into this now. But take away point, for gas molecules and solar radiation, Rayleigh scattering happens, and it is defined by forward scattering equal to backward scattering. But for aerosol particles or crowd droplets, it's not the case. Particle size is larger, and it is equivalent to solar radiation wavelengths. then the pattern gets complex. For example, if you are looking into this, which is a case for aerosol scattering, what is scattered in the forward direction is much larger compared to what is scattered in the backward direction. And you will also see some spikes up and here and there, right? There are some spikes here, here and all. This is called as lobes. There are side lobes happening in scattering pattern when it is me scattering. You will see forward scattering not equal to backward scattering. And if you are having a slight change in particle size or wavelength, this pattern may shift entirely. So you are not able to define a consistent scattering pattern for such particles. This increases the complexity of quantifying scattering in radiative transfer problems. We'll get back to that again later if we get time. Now, we have talked about radiation getting extinct when it passes through a medium. There is also a possibility of radiation getting added up in the medium. Right? We are talking about atmosphere. Light is passing through the atmosphere. Now, this atmosphere is also not at a temperature of 0 Kelvin. It may be 0 degrees Celsius, but not 0 Kelvin. It means it will also be emitting some radiation. In that case, the medium also should be emitting some radiation in the forward direction. So other than the light getting extinct in the medium, you also have a possibility of medium emitting some radiation. What happens under such conditions? This, if you are accounting for the extinction and scattering, what you are getting would be your simple radiative transfer equation. How much difference in light is happening when it is accounting for the light getting extinct and light emitted by the medium. But for that, we need to know something else. This is the thermal emission. How do you explain emission from some body with temperature greater than 0 Kelvin? This should be known to us. And this will also explain how we are getting these curves. So let's try to figure it out. Maybe I'll write something in the board now. So I should unplug this, right? Fine. So maybe I'll write it there. If it is greater than 0 Kelvin, it will emit radiation. This is the simple principle that you have to keep in mind. Now, how do you quantify this? We will be talking about some emission happening, maybe atmosphere, maybe surface of the earth, etc. So we have to define a surface to describe how much emission is happening. The body may also be a surface. Fine. So how do you describe that, or how do you put it in mathematically? We have to find out how much radiation is emitted, how much energy or power is present in that emission. We will say how much power is present in the radiation, and how do you present that? If it is a body, if it is surface like this, how much radiation is emitted by it from unit area from the surface? You may have different areas, surface areas, but that's not a good way to do it. So we always bring it to unit area, how much emission is happening. Power by unit area, and it can also emit in different wavelengths, right? So that solar radiation is not in just one wavelength, it can be along a large set of wavelengths. So you will represent that in unit wavelength. And there's also another feature. If you have a surface like this, and if it is emitting from here, this particular unit area, it can emit in this direction, this direction, this direction, or this direction. You will have an entire hemisphere for emission. So you have to write here area. Or area you already written. Sorry. I'll write this as direction. Now let's try to put some units here, which will help us define it better. Power, I'll write it as watt. Watts. Area, I'll write meter square. Wavelength, I'll put it in meter, I can write it in meter, but it's better since we are talking about solar radiation, terrestrial radiation, etc. Put it in direction. How do you write that? Angle, what angle is that? We're talking about hemispherical emission. It should be what? Whatever I am writing here, is a 2D angle. But emission happens in a 3-dimensional angle. This would be a solid axis, which is having a unit of steady, right? This is our fundamental parameter to describe emission from a surface due to thermal emission. This particular term is called directional spectral emissive power. Directional spectral emissive power. Directional to say that it is happening in one particular direction. Spectral to say that it is happening in one particular wave. And emissive power, power times U plus voltage. Okay. Now, this is one way of representing how much emission is happening. But there is one issue related to this. We're talking about a surface which is emitting. You will see that if you are looking into it like this, suppose you are having emission from this, and keeping it like this, you can see this entire area of this rectangle, right? You can see that this is a full rectangle. If I keep it like that, do you see it? You don't see anything. If you keep it like this, you can see some part of that. So it means if it is normal to you, you can see it fully. If I tilt it a bit, you won't be able to see it. If I tilt it fully, you will see nothing. So there would be similarly an angular dependence of this emission aspect, like this. You can imagine it like this. If you are having a source which is emitting from here, maximum would be in an angle normal to your eyes, and put a larger arrow here. Here. If I tilt like this, it may be a smaller angle, like this. If I keep it like this, you won't see anything, right? Just a dot. So ideally it would go like this. Emission would be like this. This describes your Lambert cosine law, if you have read that. You read that, Lambert cosine law. Or you can keep it this in mind. The emission from a surface, for example, you will be talking about Lambertian surfaces. When you talk about light emitting devices or light emitting diodes, you have to take care of all these things. This causes a problem. You don't have emission, the grazing angles along the surface. This means, other than this power area wavelength direction, the angle in which it is emitting is also affecting your emission. So we want to get out of that. We are trying to come up with a term which tells you the property of that surface. This doesn't really let us do that. We have to get out of this angular dependence. If you check that, you will see that this is a cos theta dependence. Okay? So it's a cos theta dependence. So what we can do is, here when we are describing this term, if you divide that by a cos theta, you can remove this dependence. If you are dividing this particular term with a cos theta, you are removing this cosine theta dependency. This gives you a new term instead of directional spectral emissive power, which I will write as E lambda dash of theta. Instead of this, if I divide that by E lambda dash by cos theta, where would I write? Here. E lambda dash of theta by cos theta. Now I have a new term which I call as I lambda dash, which is intensity, which doesn't look like this, but which would look like this. This is not independent of that angle. Now you are able to describe the property of the surface itself, independent of the angle of emission. So those are two terms which you can use according to requirement to describe how emission is happening from a surface. So we have two terms, intensity and spectral emissive power. Fine. Now this is again not something that you want. Imagine that you are having maybe a sun, you are trying to quantify how much emission is happening from sun. You don't really worry whether it is happening in one direction or not. You want to see if Earth is here and sun is here. You are not trying to figure out what is coming from this particular solid angle at all. You want to see what is happening from the entire sun or the entire solid angle. Right? So you don't need this. Okay. You want to get out of that sterility dependence and come up with a term which will be watts per meter square per micrometer. This is something useful to us. How can we derive that? Let's try to write it here. Let's not get into the derivation here, but I will just tell you what is happening here. If you have E lambda dash of T, which is watts per meter square per micrometer sterility, you have to remove that angle dependence. Let's integrate it across the solid angle and have a d omega here. Okay. This would give you a new term, watts per meter square per micrometer. This integration is across the solid angle, which means you have two integrations. Solid angle would be having, like you are trying to sweep across an entire sphere, right? You are not talking about a circle, which is 2D angle, covering the entire 2D angle. This is about a sphere. You have a point, and around that, it would be a sphere. And this sphere can be represented using two angles. If you are looking into the spherical coordinate system, there will be two angles. Theta, which is to the normal, which would look like this. We are looking at this. What is the angle being to this? It will look like this, how it is being. If it is like this, you see it is normal to the surface. If it is like this, it is parallel to the surface. It can vary like this, which is 0 to pi by 2. 0 to pi by 2 is your theta variation. And then you can also have, if you project it down, phi, which is an angle that defines how it is sweeping across the surface. So if you have this theta variation and this phi variation, you are able to account for the entire sphere. So your integration would be along theta and phi. But let's not do that here. You can take
entire hemisphere.
It is an entire hemisphere. Because you don't really have to worry about what is happening at the bottom. You are talking about the surface, right? So it is an entire hemisphere. That's why we are having 0 to pi by 2, not 0 to pi. So when you define this, when you do this integration, you will get a term watts per meter square per micrometer, which, if you put it mathematically as a function, will give you a new term. This would be E lambda E lambda. I no longer need this dash because it is integrated across the solid angle. Now to describe emission from surfaces or happening because of temperature, what we usually do is we define a fictitious ideal surface, which is called as a black body. Black body is considered as an ideal surface which emits the maximum radiation and which absorbs the maximum radiation. If you have a real body and a black body, maximum emission would be coming from the black body. Emission from the real body could be compared with that of black body. That's the reason why we are coming up with this black body emission. If you know the temperature, you can calculate how much emission is coming from a black body. And then you use some property of that surface to scale it down to its emission value. Now it means I can write this for black body emission as E lambda B. Emission from a black body, which is this watts per meter square per micrometer. You can write this mathematically as 2 pi h c square by lambda raised to 5, 1 by e raised to hc by lambda t minus 1. This is the Planck's black body emission spectrum. This particular equation. And this would be for some temperature aspect. You will see that it is dependent on two terms only, lambda and t. So based on the variation in temperature, your emission would change. And you also see that if lambda is varying from 0 to infinity, you will be getting different values. Now let's try to plot this here. Can you see if I draw it here?
Yes.
You're putting lambda here and E lambda B here. What do you think it would look like? This is what we saw in the first graph. When you define that absorption, it would look like this. Okay? It is watts per meter square per micrometer. The characteristics that you can see here is it is not touching 0 unless it is at some 0 temperature or something, and it has an infinite tail. It is not touching x-axis at any of this wavelength range. It will touch that only at t equal to 0 and lambda equal to infinity, not anywhere here. And it also has a characteristic peak. It is not symmetric. Right side it is skewed. It is not normal distribution or something. It is skewed and it has a rightward longer tail. And particular wavelength where its peaks would be of interest to us. We'll come back to that soon. Is this clear to all of you? Yes. So this is your Planck's black body emission spectrum for a black body of temperature T. It would look like this. Now let's try to figure out something from this. For some reason we are interested in finding out what is this lambda. Let's say lambda max. For some reason, we want to figure out the wavelength at which it is peaking, and it has a maximum. So if you are given a function, if you want to find out its maximum, what should we do?
Difference in 0 second derivative.
So this, if you are looking into this function itself, its derivative, its rate of change with time, it would be positive in this side because it is increasing. It would be negative in this side because it is decreasing. But exactly at the top, this is constant. So it should be 0. Derivative will be 0. The same would be there for a minima also. You don't have to worry about that here. But for minima also it would be 0. Now we will take derivative of this function with respect to lambda to find out what is the maximum of this function. If you do that, you are taking d e lambda b by d lambda. You will figure out something after simplifying all these things. You will see that it gets simplified into something called lambda max into t equal to some 2898 micrometer Kelvin. This still won't be sufficient for you to tell whether it is maximum or not. You have to take its second derivative and show it as negative. But let's not do it now. But this would be the final expression that you would get, where lambda max can be calculated. This would be your second law for black body emission. This is your Wien's displacement law, which connects temperature of a black body and wavelength of emission, wavelength where its peak emission happens. Now it is called as Wien's displacement law. Wien's displacement law. What would be the displacement that is happening here? What you can see is, as temperature increases, lambda max would come down. As it decreases, it increases. Your Planck's black body emission spectrum, if you try to plot here for different temperatures, you'll see that it goes like this, goes like this, goes like this. It is getting displaced. It is shifting. The lambda max is shifting as T1, T2, T3, T4. T1 greater than T2, greater than T3, greater than T4. What can you see? The peak is shifting to the right side as temperature decreases, or the peak is shifting to the left side as temperature increases. The magnitude of the peak also is coming down as temperature is coming down, which is quite understandable. Right? If you have more temperature, you are expected to have more emission coming from it, which you can see from this. This will also explain to you later why Earth's radiation spectrum.
Sir, can you hear me?
Very different. If you remember those probes,
Hello.
you will see that it looked like this. This was solar radiation spectrum, and somewhere around here, that's radiation spectrum. Now you can understand that. This is coming from a body which is of about 6,000 Kelvin, and this is coming from a body which is about 300 Kelvin. So as per Wien's displacement law, this would be having lambda max lesser than lambda max for Earth. So this is a very useful tool to figure out many things in atmospheric science studies and radiation balance problems. Fine. Once this being told, the next question that would be interested in, what is the net power or emission coming from a black body, irrespective of or accounting for all the wavelengths? We need to figure out, not just in one particular wavelength, but for all wavelengths. What is the emission coming from it? Before that, I will put some question here. I haven't drawn these curves with an intersect of any of them. They don't intersect. There are 4 curves, but none of them intersect anywhere. Please think about why it is not intersecting, or if it intersects, what would it mean? Okay. You can try it out later. Please think about it. It would be helpful for you also as a thought exercise. Okay, now coming back to this. We want to figure out what is the total emission happening across the entire wavelength. We got this by integrating across all solid angles. Now we are trying to figure out integration across all wavelengths. Or in other words, we are trying to figure out integral of this function. So just nothing else but area under this curve. So we want to figure out what is the area under this curve. So what should you do? You should integrate E lambda B with lambda.